Hello, this is Mr. Collier, and today we're going to look at the derivative and what it means. Okay, so if we look at a straight line, and we look at the slope of a straight line, notice the slope of this particular line is 1. And no matter where we look on the line, we have a constant slope of 1. Okay, so we always have a constant slope of 1 on a straight line. So how about if we have a function that is a curve? Well, we can find the slope of a curve as well by using some of the same methods. I'm going to plot some points on here. Let's look at the slope at the point 2 here. So one way to think about a slope is to look at the rate of change between 2 points. So let's try that. Let's select this point and this point. So I'm going to select these 2 points, one at 0 and one at x equals 2, and then I'm going to calculate the slope. So you see the slope here is 2, okay, but it's really the slope of this blue line right here, which is not actually matching the slope here. So another thing we can try is maybe moving this closer till it's kind of parallel with this point right here, and then checking out the slope is 3.6, right? If we want to get more accurate, we can get closer and closer to the point 2. Now we see the slope is about 4.1. And if I zoom in, I get it closer. Now it's about 3.9. Okay, so it looks fairly close to the slope at the point 2, but if I zoom in, you can see it's not quite matching up, so I can keep getting closer and closer to the x value of 2. And if I zoom in, you can see I'm still not totally close to it, or it's not 100% accurate. Right now we have the slope is 3.97. So if I keep doing that, I can get more and more accurate estimation for the slope. So now it's 3.99. Okay, you might guess that the slope here is going to be about 4. But what you do is you can keep doing this process infinitely, or we can use calculus. So calculus is a way to kind of do this process but do it infinitely, and we have methods for that, and it's called the derivative. So the most accurate representation of the slope at a point on this curve is going to be the slope of what we call the tangent line. So a tangent line is a line drawn so that it touches the curve at exactly one point. Okay, so here this is the tangent at x equals 2. Okay, if you zoom in, you will see that it touches at exactly one point. Well, I say it's kind of hard to see, but it touches at exactly 1 point. Okay, so there's the tangent line. You can see up here in the equation of the tangent line, the slope is 4. So we can say the slope of the tangent line at x equals 2 is 4, or we can say that the derivative of the function at x equals 2 is 4. Okay, and we can move this around a bit. If I move this to, let's move it over to 0 here. So the tangent line is horizontal, and the slope is going to be 0. So you can say the slope of the tangent is 0, or the derivative is 0 at x equals 0. If we go to 1, we have the slope is 2. If we go to 2, the slope of the tangent line is 4. If we go to 3, the slope of the tangent line is 6. If you go to 4, the slope of the tangent line is 8. So you might be able to start to recognize a pattern here. Okay, so we're going to go back to that in a second, but first let's look at a couple of problems here. Firstly, let's look at this problem. This is distance versus time of a cyclist. Okay, so if you get the slope of a distance time graph, you're going to get the velocity, or the speed. So if you want to get the instantaneous speed at t equals 4, we draw the tangent line and get the slope. So the slope of the tangent line here is going to be equal to, well, let's look at the change in y is 40 meters. And the change in x here is 7 minus 2 is 5 seconds. So you're going 40 meters in 5 seconds. So it's 40 meters divided by 5 seconds, which is 8 meters per second. So that is the speed of the cyclist at 4 seconds. Okay, and you can also see that if you draw a tangent line up here at 7 seconds, you see that this cyclist is going faster at 7 seconds. So the slope of the tangent line at any point gives you the instantaneous speed. Okay, if we look at this example, water is leaking from a tank. The amount of water left in the tank is measured in thousands of liters after X hours. Is given in the graph alongside how much water was originally in the tank. Okay, so the amount that's initially in the tank would be here. The y-intercept is the initial amount, which is 8,000 liters. Okay, don't forget it's in thousands of liters. How much water is in the tank after 1 hour? That would be 5,000 liters. And see how quickly was the tank losing water initially. That's the rate of change, or the slope of the tangent line in this case. So how quickly is it losing water? We can get the slope right here. So we can get the slope of this tangent line. And I guess we could use, maybe, let's look for a good point to use. Maybe this one? So the slope would be, okay, they lost about 1, 2, 3.5 thousand liters, or 3,500 liters in 0.5 seconds. So that's about 7,000 liters per second. Is that second? That's hours, sorry. So they're losing 7,000 liters per hour initially. Okay, and then the rate slows down later on as well. How quickly was the tank losing water after 1 hour? So after 1 hour, then we would draw the tangent line here. So let's try to get a nice straight line through here. I'm going to use a black line again. Alright, I think something like that might be a good tangent line. Alright, so to find the slope of that, we can try to find a nice point on the line. Here we go, that's pretty good. So that is 1 hour. 1 hour is the change in X, and the change in Y, we went from 3,000 liters to 500 liters, so that's 2,500 liters. 2,500 liters in 1 hour. Okay, and actually the slope, actually both of these lines, what I should have said is negative, so we actually have, this is negative, which means the amount of water in the tank is decreasing by 7,000 liters per hour, and then this one here, we're going to have 2,500 liters in 1 hour. So the amount of water is, decreasing by 2,500 liters per hour after 1 hour, and it keeps decreasing. Alright, so now we're going to go back to that, back to this graph here, and we're going to work out the slope of the tangent for any value of x, basically. So you see the slope changes. Here it's 4, here it's 6, here the slope of the tangent line is, well, 8.2, or if I put it right on 4, it's 8. Okay, so the slope of that tangent line is constantly changing. Okay, so here we have, let's look at it again, let's look at 0 first. So at 0, the slope of the tangent line is 0. So on this graph here, for the gradient of the tangent, or the slope of the tangent, this is going to be 0. Okay, so next we're going to look at 2. When x equals 2, I'm going to move this tangent line over to 2. And we have here the slope of the tangent line is 4. Okay, if I move this tangent line over to x equals 4, the slope of the tangent line is 8. And then we can do the same thing for -2, For negative 2, we get the slope of the tangent line is negative 4. And if we do that as well for negative 4, we'll get negative 8. Okay? So this is our function. F of x equals x squared, or y equals x squared. And this here is the slope of our tangent line. Okay, so we can call that, it's got a name. It's actually the derivative of the function, so we can say that. Or we could say this. Or we could say, also we have another notation as well, dy dx, which means the derivative of y with respect to x. Because all those mean the same thing. They mean the slope of the tangent line. So if we look at the tangent line, when we have x equals 0, the slope is 0. When x equals 2, slope is 4. When x equals 4, the slope is 8. So you can see the pattern here. You can represent these numbers by the equation y equals 2x. Okay, all these numbers are twice the x value. So y equals 2x is the equation of the derivative, or the equation of the gradient of the tangent line, which is the same thing, saying the same thing. So 2x, so you can write this 3 different ways. The derivative of y is 2x, and the derivative of the function is 2x, or derivative of y with respect to x is 2x. So that's the equation that gives the slope of the tangent line. Alright, so in summary, y equals x squared, then dy dx equals 2x. Okay, you can do the same thing with these other functions. You can graph them on autograph, and you're going to check out a pattern here. So we got this one is, the derivative is 2x. For this one here, you're going to get 3x squared. For this one, you're going to get 2. For this one, you're going to get 6x. And this one, you're going to get 12x squared. This one is 4x cubed. This one, you will get 0. And for this one, you'll get 10x to the power 4.